Welcome to GetXAML. In this video, we'll understand in depth with example K-Medoids unsupervised learning algorithm. So it is similar to your K-means. In the sense, all the steps will remain same. Only one or two steps will change. What is the difference is, I will tell in the beginning itself. K-Medoids is again a clustering is similar to K-means, but uses actual data points as cluster centers. That we also call it as Medoids. Medoids means the actual data points will be taken as a cluster center. See, what is the difference is, suppose when I compute the new means in K-means, new centroids, for example, mu1, I will get it as say 1, 2. Okay. So what is the difference here is in K-means, even if there is no data point 1, 2, okay, then I can assume this is the centroid, even if there is no data point. But and then in K-Medoids, when I find say Medoid, say 1, 2, this should be actual data point. This should be the data point. This data point should exist. So that is the key difference, first key difference. Second key difference is we usually use here Euclidean distance. In the K-means we use squared Euclidean distance. Here we use Euclidean distance. Why? You'll understand once we see the mathematical part of it. Okay, we'll only use Euclidean distance because here we are not minimizing based on the within cluster sum of squares. We are actually minimizing based on the calculating the Medoids distance from each other points. Okay. So the algorithm remains same. In the first step, you specify the number of clusters. In the second step, initialize some Medoids. Say, for example, M1, M2, like that. So 0 indicates the initialization. Okay, first 0th iteration. Assuming data points to the assigning data points to the clusters. So this again the third step remains same. Now you based on the Euclidean distance. So you assign those points which are closest to its Medoid. Okay, and then that becomes the cluster. Now only in the fourth step you change it, basically how you compute the new Medoids. Okay. So it is not like your K-means computation of centroids. It will be little bit different. That we'll see mathematically. And then to proceed until you get the convergence. Again, the convergence criteria remains same as K-means. Either all the clusters means or Medoids remain same, or your cluster assignment will not change. So till then we will repeat 3 and 4, step 3 and 4. So working is similar to K-means, only how you calculate the Medoids differs. Now let us see the mathematical part of it. It is very simple, just like your K-means. So let us assume number of clusters K. So you know how to find this K. There are different methods to find the initial number of clusters or required number of clusters. The second step, initialize the Medoids randomly. So take some data points in your data set and then initialize the Medoids. Let us represent them as M1, M2 to Mk because there are K clusters. So we will have K Medoids in the initial step. Third step is again compute the distance. So here we will compute the Euclidean distance. We will not go for the squared Euclidean distance. We will only compute the Euclidean distance between the Medoid and the all the points, and then assign based on the minimality, okay, which is the minimum distance. So what I am doing here is take this point, for example, check the Euclidean distance between this Medoid and then this Medoid. So out of this, which one is minimum? You assign that point to that particular cluster, whichever Medoid it is close to. Only thing the difference here with K-means is I am just calculating the distance, Euclidean distance. So how will you calculate the example? So if there are 2 points, say A1, B1, and say 2-dimensional C1, D1. So here we are taking the square root of A1 minus C1 whole square plus B1 minus D1 whole square. So here we are not taking the square distance. So this will give me the Euclidean distance between those 2 points. Now in that Euclidean distance, you find out the minimum. So argmin, find that cluster that it belongs to, okay, which has minimum. The logic is simple. So intuitively what I am doing, for any point in the data set, I am calculating the distance between all the Medoids and then finding out minimum distance in that Medoid. That is the meaning of the statement, and then assign to it a particular cluster. Okay, now the update step or the Medoid recalculation step changes compared to your K-means. Here what I am doing in the K-means, basically we were finding the trying to minimize the within the cluster sum of squares, but here The idea is simple. What you do is, so when I recalculate, in the recalculation in the K means I am finding the average, that is mean. So I will take number of the length or number of points in that particular cluster Ck, and then the average, all the points in that cluster. So that is the how I find the average. But this average in K means may be actual data point or may not be actual data point. But here I have to calculate the Medoid. Medoid means should be actual data point. How will I find this? So you assume each of the data points in that particular cluster. So for example, this is one cluster. You take a point, so say xi. This is a point, say xi, and then you calculate the distance with every other points, assuming this is my Medoid. Then calculate the distance, take this sum. Okay, that's what we're doing here, sum in that particular class, assuming xi as the Medoid. Okay, you calculate the sum of all the distances, Euclidean distances from that particular Medoid. Okay, so for each point you go on doing like that. For all points you assume as the Medoid and then calculate the sum of the distances from that particular Medoid, assumed Medoid. Then you find out which will give you the minimum sum. The one which gives the minimum sum will act as the new calculated Medoid, and this point will always be present in the data set because you are already assuming the point which is already there. That is how you calculate the Medoid. This is the major difference between K-means and your K-Medoids algorithm. Okay. Now again the stopping criteria remains same. So convergence will occur, else you repeat the steps 3 and 4. So when will convergence occur? If the recalculated Medoid, okay, in the next iteration is same as the previous Medoid for all the classes, or cluster assignments does not change. So that is the stopping criteria. If any one of these happens, then you converge, you stop. Else you repeat steps 3 and 4 recalculation. Okay. So that is the mathematical understanding behind your K-Medoids algorithm. So now let us see an example. The same example for our K-means I have taken here. So let us see, these steps remain same. This step 1, assign the number of clusters, how many clusters I want. Say for example, here given there is 2. This step 2, initialize the Medoids. So let us represent M1 because I have 2 clusters, I need 2 Medoids. M1 0 indicates the initialization, that is the 0th iteration. So let us give it as 1, 1. M2 0 is equal to 5, 4. Now we'll see the step 3. Step 3, the 0th iteration p equal to 0. So let us go for a table approach. It will be easy for calculation. Xi. So there are 2 Medoids. So let us say distance d1, d2. And then cluster we assign them. In step 3 is cluster assignment. Now how will you calculate d1? So K means it was different, some squared Euclidean. Here it is just Euclidean. So dn is, so for example, I have taken x1 as 1, 1, x2 as 1, 2, x3 is 4, 4, and x4 is 5, 4. And here Medoids are assumed as m1 is 1, 1, and here m2 is 5, 4 to 0. I will calculate the Euclidean distance between this x1 to m0, m1. Okay. So how will I calculate? It is square root of 1 minus 1 whole square plus again 1 minus 1 whole square. So this is 0. This becomes 0. x1 to m2. It will be square root of 1 minus 5 square plus minus 4 square. So this is square root 25 or equal to 5. So this is 5. So now check out the minimum. Which one is minimum? So d1, that means to m1. x1 to m1 is the minimum distance. So I will select assign this to cluster 1. Similarly calculate for x2 m1 and x2 m2. So this will get it as 1 root 20. Again this is the minimum. So assign it to cluster 1. This will get it as root 18 1. So 1 is the minimum out of root 18 and 1. So it is closest to Medoid M2. So cluster here will get it as 5, 0. This is closer to C2. Okay, now you have to do the class assignment. So class assignment, how will you do? So for cluster assignment, C0, the 0th iteration or initialization. So you will get x1 and x2 two data points for cluster 1. For cluster 2 initially will be x3, x4. So that is our step 3. Now in step 4, we have to go for updation. So how you update? I have to find the sum of, you have to find the sum of all the Euclidean distance for assumed medoids. Now let us take for C1. So C1 initially contains, the cluster C1 contains x1, x2. Okay. Now we assume, so what is the rule here? So step 4, we have to assume each data point in that particular cluster as the medoid and then check the distance. Find the sum of all the distance and then choose which one produces the sum of minimum distances. That is, let us take x1. So let us mention xi and then the total distance. This is what is the minimization step. Okay, that is what I am doing here. Total distance. So xi initially take x1 for this cluster C1. x1 is 1, 1. What is total distance between x1 to x2? Because there are only 2 points here. Okay. So what is the distance? I will get it as 0 plus 1. So this will be 1. So again calculate the Euclidean distance from x1 to x2. That is the meaning here. And then if you assume x2 as the medoid, I calculate the Euclidean distance, sum of Euclidean distance from x1 to x2. Because there are only 2 data points and one I am assuming as the medoid. There are 3 data points, then you have to calculate sum with from x1 to x2, x1 to x3. Add them and then find the minimum. So this will be again 1 plus 0. So this again I will get it 1. So out of this I have to find the minimum. So both are equal. So let us assume the new medoid. Okay, m1, the first iteration, sorry, is equal to x1 because both points are equidistant. So I can assume any one of them as medoid. Next, similarly for your cluster 2. Cluster 2 contains 3, 4. We calculate again the Euclidean distance from assumed new medoid to all the other data points. x3 is 4, 4. 4 is 5, 4. The total distance I will get here as 0 plus 1, it is equal to 1. Here I will get 1 plus 0 equal to 1. Again, there is a clash, so both you choose one of the minimum of this. So I can choose any one of them. So let me choose x4. So new medoid for cluster 2 is x4. Okay. So now you go for step 5. Check whether I can converge. What is the convergence condition? So initial m10 is it equal to m11 in the next iteration? Yes. Initially we took x1 as the medoid 1, 1 and then m2 is x4. So m2 is equal to 1. So this is I can converge or can check for c1 not. Initially it was equal to x1 x2. So after this again I will get the same. This is also equal to in the next iteration, so I'll get the same x1 x2. That's what we are seeing here. So this is also true. So I can stop here at this point. Okay. So this converges. So this is the final assignment. This is the final assignment for the cluster medoids and the cluster assignments, data points in their particular cluster. Now if you compare K-means versus K-medoids, you already know the advantages and limitation of K-means. K-means uses mean, the centroids. Sensitive to outliers, you already seen it in the previous video. K-medoids use medoid. Medoid means actual data point in the data set. Robust to outliers. This is the advantage of the K-medoids. It is robust to outliers because it considers actual data points. K-means is faster, simple, arithmetic mean. K-medoid is computationally extensive because when I minimize and find a new medoid, I have to compute all pairwise distances. Okay, all pairwise distances. If there are 10 points, I have to assume each 10 points as the medoid and then find the sum of distance from that particular medoid, assumed medoid. So it has to happen for all the 10 data points, for example. Okay. So this is little bit computationally intensive. K-Medoids is intensive compared to K-means in terms of computations. So both require predefined K. This is the limitation of both the algorithms. So thank you for watching. Please like, subscribe and share. We'll continue in the next video.